Okay, now we're going to do unsymmetric bending, starting with problem 4.128, which is the figure on the left. So let's read this problem statement. The couple M is applied to a beam of the cross-section shown in a plane forming an angle beta with the vertical. Determine the stress at point A, point B, and point D. Okay, so they already told us a Y, so let's say this is my positive Z direction, so that my X is pointing out, as usual, and we want to basically decompose this. We want to know this angle right here, which is 30 degrees, 30 degrees. Okay, so what's the first thing we want to do? Well, this is a case of unsymmetric bending. So we know that the overall formula for a specific point is going to be equal to minus mzy over iz plus myz over iy. And some of you might be asking, well, why does one have a minus and one doesn't? Well, if you think about going in this direction and having a moment about y that is positive, so like this part would be in tension and this part would be in compression. So you don't need that negative. And so here you don't have a negative. Here, on the other hand, you do need it, because if you think about going on a positive with the right-hand rule moment in this direction, as you go up, you're going to be compressed. And as you go down, you're going to be in tension. So what do we need in order to apply this formula? Well, we need a couple things. First, we need IZ and IY. So first, find the area moments of inertia. So we have the cross-section here. So about the z-axis, we're going to have 1 over 12, and our base is going to be 0.4, and our height is going to be 1.2. And about the y-axis, they're going to be swapped. So our base is going to be 1.2, and our height is going to be 0.4 to the third. So let's calculate those. 1 over 12 times 0.4 times 1.2 to the third. That's going to be 0.0576 inches to the fourth. And the other one is going to be, well, let me plug that in, 0.0064 inches to the fourth. Okay? So we took care of this first step. Now, the second step is, because I just like to look at the formula and I'm like, okay, I got this. Well, what else do I need? Well, I need these two. So what are we going to do? Well, we're going to say decompose the moment along our reference axes. And so we're going to have, and this is where I tend to make a mistake. This is pointing in the negative z direction, so this moment will be negative. So here I'm going to have 400 cosine of 30 degrees, which is going to be 200 square root 3 negative. I told you I was going to make a mistake. And here it's going to be 200 positive, because it's pointing in the positive y direction, right? It's pointing like that. So let's write that down over here. M sub y is equal to m sine 30 degrees, which is 400 divided by 2, which is 200 pounds inches. On the other hand, m about the z-axis is minus m cosine 30 degrees, which is 200 times the square root of 3, which is 346.4. 346.4 pounds inches. Remember that negative. Then the part 3 is we need to know if the distances of each point from both y and I don't need that comma, and z axes. So what is the distance of A along the y? So from the z-axis is 0.6. So y of A is going to be equal to y of B, which is 0.6 inches, right? Y of D is going to be minus 0.6 inches. Now, Z of B is going to be equal to Z of D, and it's going to be minus 0.2 inches, minus 0.2 inches. And so then we have to look at Z of A. It's going to be positive 0.2 inches. And now we have everything we need because we need to find point A, point B, and point C. Now we just found these for each. So now we can say that the sigma at A is going to be equal to the minus mz, which is minus 346.4, times our y, which is 0.6, divided by our iz, which is 0.0576, and these are inches, pounds over inches squared, so PSI. But don't forget to add that second part of the formula, which is 200 times, now it's going to be my z at A, 0.2 inches, divided by my iz, which is IY, sorry, 0.0064. 0.0064. So what is that going to be? Well, it's going to be 346.4 times 0.6 divided by 0.0576 plus 200 times 0.2. All of this, no, just wanted this part, divided by 0.0064. And so what we get is 9.86 KSI. And since it's positive, it's going to be in tension. We do the same thing for B, but let's see what we're going to have. Well, these are not going to change, right? The only thing that's going to change is the position of B. So what is the position of B in the y direction? Is 0.6, and in the z direction is minus 0.2. So I can copy what I had before and just insert a minus. And we're going to get minus 2.64 KSI. So that's compression. And then finally, we do the same thing for the point D. And again, the bottom is not going to change. And the moments are not going to change. It's only the position that changes. Well, what's the position y? It's negative 0.6, and the z for d is negative 0.2. So since this is going to stay negative, and this is going to be negative, and here this was going to be positive and positive, and the magnitude number is the same, we're going to have the same magnitude in the opposite sign. So minus 9.86 KSI into compression. And now that we have this, we can kind of reason through the stress distribution and say, hey, it's at a minimum at D and at a maximum at A. So if you were to look at it from the side, and this is my A and this is my D, it would kind of look like this. It's difficult to see in 3 dimensions though, because it would be a plane. But that's the idea. So I hope this was useful for you to kind of reason through. And then we could use the formula to find the neutral axis orientation. But we're not going to do this in this particular exercise. We're going to do it later. But I hope this was useful. It definitely was for me, and I'll see you next time.